Two. Thank you. All right. Where are we at now? Just have to figure out where I put it. There we go. Okay. Oh yeah. All right. Chem 11. Yes, yes, yes. Where are we at? Thank you. Now, I cannot remember. Did you guys watch the show the weekend? I can't remember what I assigned you. Yeah? Yeah. Okay, good. Good, good. So, and let's see. We did that. We were doing ions and Bohr models. Oh, let's go here. Let's see what we do. Hi. Pardon me? No, it was for homework, I think. Let me just look. I'm trying to figure out what was for homework. I'm looking. Just watch video on pages 23 to 24. Yep. And fill it in. Okay. That's okay. Don't worry about it. All right. So we made it up to page 40. 41. We'll leave that. We'll leave that. Okay, let's go to page 51. 51, 5-1. Fifty-one, 5-1. 5-1. I don't know. I'll figure that out at some point today and let you know. All right. An ion is an atom or a group of atoms with a net. What does net mean? Overall what? Charge. In a neutral atom, what can you say about the number of protons and electrons? They're the same. What can you say about in an ion? Protons and electrons are different. What is the charge of a proton? Positive. What is the charge of an electron? Negative. If the number of protons and electrons in an atom are not equal, then the atom will have either an overall positive or negative charge. What do we call this? This is an ion. Excellent. Why do atoms form ions? See if you can answer that to your neighbor. Why do atoms form ions? Alrighty. It turns out a filled outer shell is very stable. Atoms will gain or lose electrons in order to have this stable filled arrangement. What is the outer shell also called? The valence shell. Atoms with 5 or more electrons close to a valence shell, full shell, are they going to gain or lose electrons? They will gain electrons. Atom with 5 or more valence electrons are all nonmetals. When an anion is formed, what happens to the ending of the name? It becomes "ide." So basically you take the first syllable of the element and you add "ide" to the end. So almost every single anion has a 2-syllable name. Oh, hello. You can see what regular chem is like. You're like, oh my god. Okay. Sorry, he's in the enriched class, and it's a different world, isn't it? Different world. Okay. So we have the so if we have phosphorus, it does not become phosphoride. It's just the first syllable, phosphide. Hydrogen does not become hydrogide. It just becomes hydride. Oxygen becomes, okay, everybody, oxygen becomes, nitrogen becomes, phosphorus becomes, hydrogen becomes, okay, so just 2 syllables, take that first syllable, add "ide." The only one that doesn't do it is selenium, but you're hardly ever going to come across that. Selenium is selenide, okay? Eh. All right, so here we have a fluorine atom. Of course, we have our little empty space there. Along comes an electron and fills that empty spot, so it gains 1 electron. And if you gain a negative charge, what does your charge become? If you gain 1 electron, what is your charge? Is it positive or is it negative if you gain an electron? You gain a negative thing, so it becomes negative. How much negative? -1. Okay, so just 1 minus. Now, if you look at it from the overall net charge perspective, you can say I have 9 protons. The protons does not change. I go from having 9 electrons to having 10 electrons. Now I have more electrons than protons, which means my overall charge is negative. So if you are taking your sulfur atom, here is a sulfur atom. It has atomic number is 16. What does that tell you? 16 protons. What else does it tell you if you're looking for an atom? 16, not neutrons. It doesn't tell you that. It tells you there's 16 electrons. It just so happens that there's 16 neutrons. Okay. So we've drawn in all of our 16 electrons. And what do you notice about that outer shell? There's a space and there's another space. Yes? Ooh. So what will happen? This little guy over here is going to gain 2 electrons. And if we gain 2 electrons, what's the overall charge? The charge is -2, or 2 negative is a better way of doing it. So if we write the symbol then for sulfur, there is sulfur. This would be sulfur with a 2 minus. What if we wanted to put those little numbers on the left? What little number would go at the top left? 32. How did we get 32? That's our protons plus neutrons. And what do we call protons plus neutrons? That's called the mass number. Not the atomic mass. Remember what's the difference between mass number and atomic mass? Tell your partner. All of them. Okay, so what is the difference between the mass number and the atomic mass? Atomic mass is the average of all the isotopes, whereas the mass number is the mass of one specific isotope. And of course, that's the protons plus the neutrons. What number goes at the bottom left of the symbol? The atomic number, so that's going to be a 16. Okay. did I forget on my Bohr model of my sulfide ion? I forgot the big square brackets. And I didn't leave much room for them, did I? Okay, we'll just chuck them around everything. And the charge. And what would the name of this sulfide? Is good? Okay. Can you guys do the next one on your own, please? Now, what group, hopefully your structure looks something like this. We went from having 7 protons and 7 electrons to having 7 protons and 10 electrons. So our net charge became -3. All right. What group is nitrogen in? Nitrogen is in group what? You can look on your periodic table. I just want the number. Group 15. What does that 5 tell you? Number of electrons in the outer shell. That is the number of valence electrons. So, what could you tell me about all anions, all group 15 anions? All group 15, they all gain electrons. They all gain how many? Gain 3 electrons. Therefore, the charge is 3 minus. So if you're looking at group 15 and you're like, what is the charge of phosphide ion? What's the charge of a phosphide ion? It's in group 15. Remember 15? What do you need to do? You need to gain 3. So what is your charge? 3 minus. So phosphorus is in group 15. What's its charge? What's the charge of a phosphide ion? Oh my God, what is the charge of a phosphide ion? I'm going to let you think about it for a minute and then I'm going to ask it again. Okay? And this includes you people over there too. I know my periodic table's here, so I'm not standing as close to you, but look at phosphorus, it's in group 15. What is the charge of a phosphide ion? 3 minus. What is the charge of a nitride ion? 3 minus. What is the charge? Arsenic is right under phosphorus. It's still in group 15. What is its charge? 3 minus. when you're like in grade 10 and 9 and they give you those baby periodic tables with the charges all over them? You don't get that this year because you know that group 15 has how many valence electrons? How many valence electrons? It has 5 valence electrons. And therefore, what does it do? It has to gain 3, so its charge is -3. Let's go back and look at sulfur. What group is sulfur in? What did I do with my... Sulfur is group 16. How many valence electrons? 6 valence electrons. Therefore, it will gain how many? 2 electrons. Therefore, the charge is 2 minus. And what can you say about all group 16 ions? Okay? What if we go back here to fluorine? What group is fluorine in? Group 17. How many valence electrons? 17 valence electrons. No, not 17. Sorry about that. 7 valence electrons. Therefore, it will gain 1 electron. Therefore, the charge is 1 minus. So when you're on your periodic table, let's go take a look at a periodic table. Well, okay, there we go. -3, 1, -2, -3. So when I tell you that knowing the charges is as easy as 1, 2, 3, it really is. It's literally as easy as 1, 2, 3. When you write a test, those will not be on your periodic table. Okay, if you want to write them on your own periodic table, that's fine, but just be aware on a test you will be expected to just know them. Okay. What about elements in group 1? They have 1 valence electron. Therefore, they will lose that electron. Therefore, they will become +1. How about group 2? +2. And then how about group 13? Plus. How many valence electrons? 3 valence electrons. So what will they do? They will lose 3 electrons. What does their charge become? +3. Group 14 forms covalent bonds, not ionic bonds, and so it doesn't gain or lose electrons, it shares them instead. Okay? And in fact, we could even say that we know what group 3 is. Group 3 is +3. Okay? And then, just for fun, there's actually like a little mini staircase in here. Okay, and it goes right here. Whoops, don't draw that line. Should only go up to here, and then there, and then there, and then there, and then there, and then there. You can feel free to draw this on your periodic table if you'd like to. Do you remember I said it's all as easy as 1, 2, 3? How many, well, you know what the charge of aluminum is. What is the charge of aluminum? 3 plus. What's the charge of gallium? 3 plus. What's the charge of indium? 3 plus. And if you wanted to make life really easy on yourself, what would you guess that the charge of zinc is? Remember, it's all as easy as 1, 2, 3. It's as easy as 1, 2, 3. 3 plus, 3 plus, 3 plus. There's 3 of them. Oh, look at that. Oh, look, there's 2 in the zinc. There's 2. What's its charge? 2. Oh, and then there's 1 here. What's the charge of silver? 1. Once again, that's something that in the next unit, you won't need to know those charges for this unit, but in the next unit, you will need to know those charges and they will not be on the periodic table that you get, but it is worthwhile learning them. So remembering your charges is as easy as 1, 2, 3. And then people always want to say, oh, well, how do I know the charges of the transition metals, all those ones in there? And the fact of the matter is that you either have to figure it out from the formula or you have to figure it out from the name. If it's in the name, you just read the Roman numeral. It'll say iron 2 and you'll know it's 2 plus. Or it'll say iron 3 and it's iron 3 plus. Okay, so don't worry about those ones just yet. They will come soon enough. All right, let's go back here to, there we are. Okay. So, where do anions get all those extra electrons from? Do they just float around in the air waiting for an atom to come along? They get them from other atoms. Who is trying to give away electrons? Cations, those metals, okay? Isn't that nice? That works out so lovely, right? The metals are all like, oh, please, 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 give me your electrons. Okay, there we go. So the metals are all like, electrons, who wants some electrons? And the non-metals are like, oh, please, we'll take them. Okay, so it's a very nice system. So any atom that has 3 or fewer electrons, in other words, closer to empty, what will they do with their electrons? They will lose electrons in order to leave their valence shell empty. Your new outermost shell will be full. Atoms with 3 or fewer electrons in their valence shell, they are all what kind of elements? Metals. That's okay. That's why we're learning. If you knew it all, you wouldn't be in this class. All right, so here's sodium. What do you see in sodium's outer shell? One valence electron. What's it going to do? Bye-bye. All right, so now we have an empty or vacant valence shell. What should I do with that Bohr model? Destroy it. Okay, if I wasn't going to destroy it though, maybe I would put it in brackets. And maybe I would also put a charge. Now, which one is the most correct? Just plus, okay? Plus is the best. Just plus. And what do we do to the name of this ion? Nothing. It does not become sodide. No sodide. You just stick the word ion on the end. Okay, sodium ion. Magnesium. We can just cross these ones out. Isn't that nice? Stick our brackets on. What will our charge be for this one here? The amount of electrons that I murdered, how many did I murder? 2, so my charge is 2 plus. So this is a what ion? Magnesium. And its symbol would be Mg. 2 plus is best. Plus 2 is okay. But you're getting to be big kids now, so try for 2 plus, please. Okay? And this one's just Mg. Aluminum. What group is aluminum in? Can you tell from looking at its outer shell? It has 3 valence electrons. What group is it in? 13. We're going to kill 3 electrons. Ah! Which gives that, oh, I'm sorry, that should have been ah. And that's going to be 3 plus. Aluminum, unless you're from and everywhere in the world other than Canada and the US, in which case it's aluminium. But I'm going to write aluminum because that's what we're stuck with. They spell it different too, yes. And in fact, that is the official spelling. Why do we? I don't know. We dropped it at some point, and the Americans, you know, like they just do their thing, and they're big and whatever. And they, anyway. Oh, what happened? That's not good. Okay, there we go. So we have Al for our atom, and our symbol for aluminum with the charge would be Al what? 3 plus. Where do cations send their extra electrons? To other atoms. What kind of other atoms? The nonmetals. All right, so we've just got our outer shell there, and in fact, what you're seeing here is what you are going to be drawing using not Bohr models, but rather Lewis dot structures. Yes? Because once you have the Lewis dot structures, you don't have to worry about the inner electrons. You just do the valence electrons and you get rid of the circle. Okay? And if I was really being good about this, I would put brackets and a plus and brackets and a minus. Why is this sideways? No. I'll let you fill that one in. Okay, why don't you guys try that one on your own? That'd be fine. Sure. Yeah, sounds good. Of course. No, come back. Close. Uh, how are we doing? Are we still working on that? Are we done? Excellent. Now, I think I had this in black diamonds because the last time I taught this course was during the quarter system and we had no time. We barely managed to get through any of this thing. I think we can all do this because it's not hard. Because you did it already, right? We did it in a POGIL. So, would we like another example or two? At least one more example. Okay, would you like to do that example with Tyler or would you like to do it with me? I got one hate Tyler, I got two love Tylers. You also love me. Oh, fantastic. Okay. Okay, I'll tell you what, we'll do one with me, and then if you're feeling like you still don't understand it, you can watch the second one with Tyler. Okay. We have gallium. Gallium has two stable isotopes. We have gallium 69, which is at 60.11%. The word abundant just means how much there is, okay? So abundance means how much there is. We also have gallium 71, which is 39.89% abundant. And the masses, now you'll notice that the masses aren't simply 69 and 71. Gallium-69 actually has a mass of 68.926. Okay, whereas gallium-71 has a mass of 70.925. Do you guys know what the word respectively means? Respectively means if you've written things in a sentence, the first one goes with the first one and the second one goes with the second one. So do you see how the gallium-69 went with this mass? Because it was the first one went with the first mass, and the gallium-71 is the second one and it went with the second mass. That's what respectively means. It means if you have two pairs of things, like number one goes with number one and number two goes with number two. Okay? So, average atomic mass is equal to, all you do is you take your percent. What do you do with your percent? You change it into a decimal. So you change the percent to a decimal. Okay, so we have gallium-69 is 60.11%. Oh, I should have changed it to a decimal because I just said I was going to do that and then I didn't. 0.6011. And then we multiply by the mass of the isotope. And what is the mass of that gallium-61 or 69 isotope? 68.926. Excellent. And we're going to do the same thing. Now we're just going to add it. Our percent for this one is 39.89. So as a decimal, what would that be? Oh, 0.3989. And then we want our mass of the isotope. And the mass of the isotope is 70.925. All right. And we're not just going to throw this all into our calculator because we need to worry about what? Figs. And guess what? We have two operations here. We have multiplication and then we have addition. So the only tricky thing about these questions is the sig figs. So let's do this. So step number 1, 0.6011 times 68.926 is equal to 41.4314. There's some numbers after that, but I'm not going to write them down. Plus 0.3989 times 70.925 equals 28.291, or sorry, 20. There we go. what operation did we just do? We just did multiplication. So how many sig figs here? 4 sig figs. How many sig figs here? 5 sig figs. So how many would our answer have if we were done at this point? We would have 4 sig figs, 4 sig figs. So which is our uncertain digit there? Is it 4? Is it the 1? Is it the 4? Is it the 3? Is it the 1? Is it the 4? What is it? What is our uncertain digit in that number? It's the 3. Okay, so that's our uncertain digit. Same thing for the next one, right? We've got 4 sig figs. We have 5 sig figs, so we should have 4 sig figs here. And who is our uncertain digit? 9. So when we add these two numbers together, we get plus 41.4314 equals 69.7234. And because we are adding, which sig fig rule do we use? The first uncertain digit, which is our second decimal place. And so that would then round to 69.72. What have I forgotten all the way through this question? Units. Oy, 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 they're gone everywhere. What have I got up here? What are my units? What are my units right up here? $69.896 AMU. And I have 70.925 AMU. What does AMU stand for? Atomic mass units. And so that would mean in my second line of my equation, I should also write AMU, AMU, and then finally AMU. Box my final answer. Is good? Would we like another example? Yes? If you do not want to do another example, you could and the Hebdens are all at the back there because I told you guys to take yours home and leave them there, right? So if you don't have your Hebden here, that's probably a good thing. On page, find it. Page 151, number 24 and 25. So Hebden. Page 141, number 24 and 25. Oh, 150, I'm sorry. What am I? No, 151. 151. There we go. So if you're feeling good about it, you can try those. Go help yourself to a book. If not, I'm going to go through another example. Okay. Yeah. We just don't round until the very end. Okay. Yeah. Just had a good question. Why do we not round these numbers? And the answer is that could possibly introduce rounding errors. Okay, so we don't round until we get to our very final answer. Okay. All right. Rubidium. two isotopes. We have rubidium 85. I'm going to rewrite it down here as rubidium 85, which has a mass of 84.911 AMU. And oh my God, I've written rubidium 85 and rubidium 85. That one should be an 87. Okay. Let me put a big star there though, so I remember to change it. And we have rubidium 87. It's a good reminder that your mass number either goes after the name with a dash, or it goes at the top left if you're writing the symbol. And that is 86.909 AMU. Oh, actually, this is a different question altogether. This isn't just finding the mass. It says, based on this information, which of the isotopes of rubidium is more abundant? Do we remember what abundant means? How much there is. Which one has more stuff? How do you know? So what is our average mass? Is 85.47. What I would do is I would draw myself a little like number line. Yeah, I'd be like, this one's almost 85, right? So I got 85 here, and I got 87 here, and then I have 86, and no, 86 is right in the middle. I can do this. 86 is right in the middle. My average mass is where approximately? It's about here, yes? That's about, this is approximately 85.5, yes? Yeah, we changed that one. Yeah, that second one should be 87. So if we look at that, which isotope is more abundant, the 85 or the 87? Which one do we have more of? Yeah, the average mass is closer to 85 than it is to 87. That's our average mass. Therefore, rubidium 85 is more abundant. We have more of it. And there is actually a way to figure out what your percentages are on this one. Anyone want to give it a go? If you would like to challenge yourself, you could challenge yourself to find the percent abundance of each isotope. Yep. Even if you can just get the equation, do you know what I mean? Like that's good. Oh. Oh, okay. All righty. Here, we'll do an actual one where we're calculating the average mass again. What? No. Well, it'll be on there as a black diamond. Yeah. Yeah. So our average mass is, we're going to take our percent abundance, 0.7899. We convert it to a decimal. And then we're going to multiply that by 23.985 AMU. We're going to take our next mass and add it on. That's going to be 10%. And 10% as a decimal is 0.1000. And that's going to be multiplied by 24.986. And then our third one we've got 11%, so 0.1101 times 25.983. So when we multiply our first one, 78% times 23 point whatever, we get 18.945, 18.9458. 4 sig figs, so that's our uncertain digit. 0.1 times 24.986. So all we need to do there is move our decimal place over one. So that's going to be 2.4986. I like that kind of math. And that's 4 sig figs, so it's our third decimal place. And then 0.1101 times 25.983, and we get 2.8607.273, sorry. And that's going to go to 4 sig figs, so that's our uncertain digit there. When we add all 3 of those together, we get 24.30512. And of course, these are all AMU, which I forgot everywhere again. AMU. And that's the nice thing. You can stick brackets around everything and put your unit on the outside, then you only have to write it once. Okay? And that's going to go to our our second decimal place, so that is going to become 24.31 AMU. You don't have to put the dots, AMU is fine, yeah. Would anyone like to see how to do that challenge? Yes? Okay, if you're not interested in the challenge, if you're like, I'm good, then try these questions while you wait for the rest of us, okay? Grab yourself a copy of Hebden, it's at the back there. You are not responsible for this next bit, it's just there as a challenge, as a black diamond. So we have, I'm just gonna get rid of this so I can do the work here. Okay, la 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 la. Yeah. So I would say let the decimal percent, let the percent of RB 85 equal X. In fact, I'm going to make it the decimal percent because that makes my life easy. Yes? I have two isotopes. So if the percent, like, how much is the total of a decimal percent? Oh, 1, right? Because the total percent is 100%, right? If we change that into a decimal, that becomes 1, okay? So then, if we only have two isotopes and the percent of one isotope is X, then the decimal percent of rubidium-85 is equal to 1 minus X. Yes? And so now we can say we have our average mass which is 85.47, that's going to be equal to our decimal percent of rubidium 85, which has that mass. So that's going to be X times 84.911 AMU. Okay, and then we're going to add to that we have 1 minus X of the rubidium 80. Oh, that should have been 87 here. Why did I write 85 again? That should have been a 7. Yeah? So there's our rubidium 87. So we have 1 minus X times 86.909. And now we just start crunching the algebra. And I'm going to get rid of my AMU here because the algebra makes it just makes my algebra untidy. Okay, we'll throw them all in at the end. Okay, so we have 85.47 is equal to 84.911x plus 86.909 minus 86.909x. And then I'm going to combine my x terms. Should have left myself more room, but I didn't. Okay, so I'm going to combine my x terms. That is 84.911 minus 86.909. So that gives me minus 1.998 x plus 86.909. So I'm going to subtract 86.909 from both sides. And I get, these two guys go away, right? 85.47 minus 86.909 equals 1.439. 2 decimal places because I got my uncertain digit here. Okay, so I've only got 3 sig figs now. Oh, sig figs are like another dimension to this, right? Equals negative 1.998x. And then x is equal to 1.439 divided by, or sorry, this was negative, right? Yes. So then I can get rid of both my negatives, okay, because I don't want them. 1.439 divided by 1.998 0.7202 to only 3 sig figs though, because this only had 3 sig figs. But like I said, that would be like another extra dimension to the question, right? That's like the challenge beyond the challenge. It's like, maybe I just do this without worrying about sig figs, and that's enough of a challenge for me. Maybe I do double black diamond to do the sig figs on that one, right? So now you're at, X was the percent of rubidium 85. So therefore, 85 rubidium is 72.0%. And therefore, 87 rubidium is 100 minus 72.0, which is 28, 28.0%. So that's like the super duper challenge, okay? So if you're like, no, thank you, I'm good just figuring out my average, then just stick with that, okay? Do we feel like we'd just like to practice those for homework? Because we're almost out of class time today. Okay, so there's these 2 questions, but if you also want more practice in your workbook, pages 63 and 64, there is a challenge question there, and you can do that challenge if you want to. It's the same as this challenge, okay? So homework. No, on a test you'd need to borrow my calculator and show your work. You do, you really do. Yeah, no. You need to be able to work through that in your head, yeah. And you do not need to do all of these questions because you could drive, I mean, it's all the same after a while. So if you're like, no, I'm getting it, you don't have to do every single question. Your Hebden should just live at home because that way you have your own copy of Hebden, don't you? So that's Hebden 12. I'm pretty sure. Let's see your book card. Okay, that can just live at home because we have a full class set here. So if you do it during class, you can just borrow it. we go. You sound very excited.
I did like her homework like seriously like 4 times to try and understand it. It's just I understand it, but it's like enough. Like it's so unrealistic. But this is what happens. You watch a YouTube video where someone who's in grade like or like first year university explains it, and there's so much more to it. Like he's just Mr. Benani's just using regular friction, like just that's it. But there's kinetic friction and static friction, and he's not using those, and it's making it weird. So this will be a fun. I hope so.
You're my favorite class. No, why would I be talking to you? No, no, I'm okay.
Favorite class that you use for every single class?
No.
Oh, really?
Yes. Molar mass with a mixture, so that would be the average. Yes. Oh, I should have said that, Matthew. Here's the new workbook. Okay, and we have our tests today. So do you want to come during flex tomorrow? That'd be perfect. Okay, you probably won't be able to finish it during flex, but we'll get a good start on it and then we'll figure out where to go from there. Okay, cool. Yeah. Anya. Hi.